Welcome everybody to INE's CCIE Data Center Kickoff vSeminar. I am Brian McGahan and I'm joined here today with Mark Snow. And we're going to be talking about the new certification that everyone is excited about, which is the new CCIE Data Center offering. So the first thing I want to mention is just what the basic agenda for the seminar is going to be. The first thing is that we're going to talk about just the overall scope of what CCIE Data Center is going to involve. We'll talk about the hardware blueprint, what are the specific technical topics that are going to be involved. And then we're going to get into more details about, at INE, what we're going to be doing for classes and for rack rentals and for lab material for you guys in order to prepare for the new certification. We'll also talk about some additional training offerings that we're going to be having that are related to data center that are not specifically for CCIE Data Center, but are going to apply to the everyday engineer that could use as a resource if you want to learn how Nexus works or learn how the new unified computing system or how storage networking works. That's going to be part of what we're talking about today as well. So the first thing is, as I mentioned, we're talking about the new CCIE Data Center track, which as of yet, the actual track is not launched yet. It's going to be coming out with first the written exam in September of this year, September 2012, and then followed shortly after by the lab exam coming out in October of 2012. Now for the specific topics that are going to be within the blueprint, one of the big, not necessarily confusions, but the big, one of the main points is that CCIE Data Center is going to be testing on very high-level equipment. So we need to talk about what are the hardware platforms that are going to be within the scope, what are the particular software versions that we're using, and ultimately that's going to lead us into what are the particular technical topics that we're going to be focusing on. So the first thing that I want to do related to the technical topics is to take a look at the actual blueprint, which we can see if we go to Cisco's website, and if you go to cisco.com/go/CCIE. Then from here, it's going to assume that you're logged in to your CCO account. So if you go down to Data Center, then there's going to be mainly two portions that we want to see here. What are the lab exam topics, and then what's going to be within the scope of the lab hardware. So if you click on the View the Lab Exam Topics, this is going to open up the separate, basically feature blueprint that's going to be what particular topics are within the scope. And then you should also see from here what is going to be the specific hardware platforms. So you can read this through in detail afterwards to get a better understanding of what are the individual line items that are going to be within the scope of CCIE Data Center. What we're going to talk about next then is what are the hardware platforms, and then how are we going to deal with that integrating for video training and for live classes and for rack rentals and so forth. So the first big thing with the hardware platforms then is going to be the Nexus series switches, where this is going to be made up of the Nexus 7000 series, whether using 7009 or 7010. Really the key is that we're using the version 6 as the software version, and it includes both the F1 and the M1 modules, where the M module is the layer 3 module, which is to do like layer 3 EHRP routing or OSPF routing. And then also some enhanced layer 3 features we're going to talk about, things like overlay transport virtualization for basically using routing to bridge traffic between disparate data centers across the country or across the world even. We also have the F1 modules, which is used for layer 2 switching solely. The key with the F1 module is that it's going to be used for a feature that's known as Cisco Fabric Path, which is similar to the new standard that's coming out that's called Trill, which is a transparent interconnection of lots of links. Basically, it's a new enhanced way that we can get rid of the legacy spanning tree in the data center and then replace it with more high availability, more flexibility as to how we're actually bridging our traffic between the different switches. We're also going to be including the Nexus 5500 switches, specifically the 5548, where the key for this switch It has what's known as unified ports, which means that it can be used for either 1 gig Ethernet or 10 gig Ethernet, but it can also be running fiber channel at the same time to go to your end servers that are fiber channel attached for storage, or it can be going to your actual storage arrays like your EMC or NetApp array, or to the actual storage switches like the MDS series of switches. We also have the Nexus 2000 series, which is also known as the fabric extenders, or the FEXs, where the FEXs are going to be connecting either to the Nexus 5Ks or to the Nexus 7Ks, where basically it looks like a line card of the parent chassis, similar to where you would have like a 6500 series catalyst or a 4500 series catalyst, where in this case, instead of having the blade physically in the chassis and using the backplane to switch between line cards, the Nexus 7K and the 5K are going to use basically 10 gig Ethernet links as the backplane in order to talk to the 2K, the fabric extender. We also have the virtual switch, the Nexus 1000V, that runs as a VMware guest inside VMware ESX, which basically means that you could run this on like your UCS blade server, series chassis, or you could run it on a standalone server that basically has the same software feature set for layer 2 switching with the Nexus NXOS, but it's going to be running as a virtualized, basically virtualized Ethernet module and virtualized supervisor module, so that we have more flexibility when we have lots of virtual machines like Windows servers or Linux servers that are running inside VMware. Then we're trying to figure out how do we actually want to attach those onto the layer 2 LAN, both for Ethernet switching and for our SAN connectivity.
So we're also going to include, of course, the UCS, the Unified Computing System, the 5108 chassis, and we'll have our B200 M2 servers, just like is on the blueprint, is called for on the blueprint. These will be controlled by and connected back to the rest of the LAN and SAN with the 6248 UP fabric interconnects, really providing all the brains and intelligence for the entire UCS platform. We will have the 6204 or possibly even a 6208 FEX, the fabric extenders in the back of the UCS chassis. And we'll certainly provide at least one, possibly multiple UCS C200, the rack mount servers. And we'll be providing additional servers as well for various tasks and connectivity, whether it be fiber channel arrays or whether it be simulating JBODs or whether it be actually used as end hosts. So we'll have the UCS, we'll have additional VMware guests and hosts on the network as well. We will have that joined by the ACE, the application control engine, basically the 4710 appliance, allowing us to do intelligent load balancing. And really, there probably won't be too much there, but we will certainly go into that quite a bit as well. So we're also going to, of course, include the MDS series, the 9222i, the I indicating that it can not only provide fiber channel, but also iSCSI connectivity as well. We'll, of course, have JBODs, or just a bunch of disks, and these will be FC attached or fiber channel attached. And we'll have the data center management software, the DCNM.
Now, one of the things that is specifically challenging with data center, especially for a lot of engineers out there that are coming from a LAN background or a WAN background, and then trying to integrate these new additional technologies, where typically in the past, a lot of the times it would be two roles in the network where you have your LAN and WAN engineers, and then you have your SAN engineers. But now with the kind of combination of these two platforms together, where the Nexus 7K or the Nexus 5K can run not only Ethernet switching and layer 3 routing, but it also does fiber channel switching for the SAN, that's going to be one of the big topic areas that the traditional layer 2, layer 3 network engineer needs to get involved with now, is the SAN switching, both from the actual fiber channel switches, the MDS components, and then also for the Nexus 5K and 7K, which is basically going to be running pretty much the same OS, where Nexus is basically the next generation of the MDS. So behind Mark and I here, what we have here is kind of a sample topology of what you could logically expect within the course of the CCIE Data Center exam. And I just wanted to talk a little bit about what are the different platforms that we're going to be using, and then specifically where do they fit into the overall design of where, what is the role of Nexus 7K, what does 5K do, what does 2K, what does 1000V do, because that's going to be really the biggest first hurdle to figure out what am I trying to solve with these platforms. So what's the overall design goal of really what we're trying to accomplish in the data center. So here we kind of have a large mix of different platforms where at the top of the network here, we have the Nexus 7000 series. We could consider this kind of the core where we would be doing our traditional layer 2 switching and then also our layer 3 switching. Where in most data center environments, this is going to be the core of the layer 2 network. And then beyond this, you go with your layer 3 uplinks, maybe to like an ASR or maybe like a 7200 series router. That this is where the rest of like the IPv4 network would be located, like the internet or maybe your MPLS layer 3 VPN. However, you're going to do connectivity actually out to the final end users that are coming like from your remote offices or from like your home users, that type of stuff. So Nexus 7K, this is mainly going to be the first entry point of where the traffic is getting into the network. Now we'll see once we get further into this and actually start exploring what are the different features of Nexus 7K, there's a lot of flexibility as to where it can specifically sit in the data center, both as a layer 2 access switch, layer 2 aggregation, layer 2 core, layer 3 core for routing. It's very, very flexible, a lot of different features that we need to focus on for the Nexus 7K. The next one down from here is the Nexus 5000 series switch, where this could be considered in kind of our traditional core and distribution and access layer design, where in most cases Nexus 5000 is going to be like our distribution layer switches, where sometimes this is also called the end of row or EOR design, where basically we have our end servers, which is going to be like our web servers or a database or applications that are talking to the access layer. The access layer here with the Nexus 2000 series switches, these are typically, the term here used is the top of row, or the TOR, where if we're talking about like our actual physical cage or physical rack in the data center where we have 42 U's of space, we're typically going to have the Nexus 2000 at the top of this rack. And this is going to be used for basically aggregating the physical wiring that are going down to the end servers. Or in certain cases where we're using like the UCS chassis, where we're doing more virtualization at the hardware level and virtualization at the actual machine level, like VMware or Zen. We basically are aggregating these together with the Nexus 2000. But the key point about this particular platform is that it is not a standalone switch. Where in traditional environments, in your access layer, you might have like maybe a 3750 catalyst if you're doing stack-wise between the different chassis, or maybe you have just some layer 2 platform like 2960 or 2950, where traditionally these are standalone switches where you manage them through the console or through your normal remote access. You're doing things like assigning access VLANs, assigning trunking. The logic of the Nexus 2K is the same, except it's managed centrally from the parent switch, which is going to be either the Nexus 5000 or the Nexus 7000. So basically what we have here is kind of a more indication of what the physical wiring topology would look like in the data center, but it's not a real good representation of what the logical layer 3 topology would be. So from like the actual end server representation, if I have like my web server here, basically this is going to look like just one big flat LAN that they're connecting to. And then we're going to have like our default gateway up here running something like HSRP or running something like gateway load balancing protocol, where we're doing our normal layer 2 switching up to the edge, up to the layer 3 edge. And then beyond the layer 3 edge, we're going to whatever the rest of the IP network is. Now, the challenge with this, though, is that there's so many different roles that these individual platforms can play. And there's so many different features that come into the redundancy of the network, the high availability, the bandwidth aggregation, and then dealing with things like how do we attach to the SAN versus how do we attach to the LAN. When we're coming from these servers that traditionally would have links that go in one direction that are going towards the regular layer 2 LAN, which means we would have like an Ethernet port here that's going to our layer 2 switches, and then we would normally have additionally our fiber channel ports that are going to be going to like an MDS or maybe like a brocade switch that is doing the fiber channel SAN switching. But one of the big changes and one of the big migrations that we're moving towards what's known as the unified fabric is that in a lot of new designs, this connectivity to the physical server is going to be combined both for the layer 2 LAN and for the layer 2 SAN. So again, this for a lot of engineers, this is going to be one of the big sticking points of traditionally I came from implementing Catalyst switches and Cisco routers, doing layer 2 switching, layer 3 routing. So how do I deal with kind of this brand new topic domain for me? What is fiber channel? What is fiber channel over IP? What is iSCSI? What is fiber channel over Ethernet? That's going to be a big portion moving forward with this particular track that we need to get involved with. So not only the traditional layer 2 LAN switching and layer 3 routing, but also some of these additional things that come into the design, like the aggregation with the UCS chassis going to the fabric interconnects. And then we're also going to be talking about more virtualization, both from the hardware level and from the software level, where inside this chassis, we may have 8 physical servers that are represented by this one chassis in the network, but we literally could have thousands of virtual machines that are running inside these physical servers. So how do we deal with taking what used to be hundreds or thousands of 1U or larger servers in the data center and then kind of collapsing those down, not only to save in things like space and power and cooling, but also for management of the overall environment. It's going to be much easier to manage these single larger chassis that can be distributed versus saying, I have to manage 1,000 Windows database servers, or I have to manage 1,000 different Apache web servers that are in the physical data center. So as we go through the different topics today and talk a little bit more about what are things like virtual port channels, what are things like VDCs, what are things like overlay transport virtualization. We're going to be coming back to this diagram and just giving you guys like an overall high-level view of what are the different pieces of the design for data center, and then how is it going to fit into just the individual pieces that we need to put together to figure out the final puzzle, which is the overall connectivity of the entire network here.
So we've put together a training strategy. And INE's CCIE Data Center training strategy is, first of all, we have to take a step back and just address the fact that overall, these topics are way too large for a single 5-day or really even a 10-day boot camp. There is a lot to be covered. There's a lot of possible variation. There's a lot of possible permutations of not only the topology, but of the technologies, how we can overlay them, how we can make them work according to tasks that we might be given. So it's not going to be possible to cover everything in a single boot camp. So what we've done is we've broken out everything into 3 main topic domains. We've broken it down by, first of all, Nexus switching, and we didn't simply call this switching because really the features and the feature set and a lot of the technologies that are going to be used are really unique, not all of them of course, but are really unique to the Cisco Nexus product line. So we're calling this our Nexus switching topic domain. The next is going to be storage, and this is going to really give you a thorough understanding, and we'll talk about how we're going to unpack different levels of this training, whether it be an introductory level, a primary level, or a more advanced or expert level. But we're going to talk about fiber channel, we're going to talk about the MDS director class and modular class switches. and really give the engineer a full understanding of fiber channel and how it fits into the data center. And not only the traditional fiber channel, which is probably, I would maybe imagine, where we'll spend most of the time, but certainly FCIP as well, so fiber channel over IP, iSCSI, which is completely different, and we'll talk about that, and then FCOE. So instead of putting fiber channel into a layer 3 header, an IP, we're going to put it directly into a layer 2 header and switch that, and multi-hop FCOE as well. And then the third portion of our topic domain is going to be the computing portion. So this will deal with the UCS, the Unified Computing System. We'll also include in here the ACE, the load balancers. There's really not a lot that we have to do there, but we do have to understand it fairly well for the CCIE Data Center exam. And this also, we wrestled with where should we put the Nexus 1000. It's really part of the Nexus switching line, but it really fits more appropriately into the computing section. We really can't have Nexus without the VMware installation on our hardware blades.
So really the key point here is that the topic scope for this exam is very, very large. And like Mark said, it's just not feasible for this to be covered in a 5-day class.
It may seem simple with the three topic domains that we've broken it down into, but the whole idea was to try to make it, present it in a simplified approach so that it was very approachable to you, the student, the candidate.
And going along with that, to make it a modular approach. Because like I mentioned, for most engineers that are out there traditionally coming from a layer 2 switching, a layer 3 routing background, you may see that a lot of stuff that goes along with Nexus is the same stuff that I've been doing for 5 years, 10 years or more. Layer 2 Ethernet switching, spanning tree, IGP routing, BGP routing, multicast. A lot of this stuff is, you know, the same topics that we've been dealing with Catalyst 6500 or, you know, our ISRs, previous routers before that. So depending on where you're at specifically in your work experience, your technology experience, you may not need to focus more on you know, the fundamentals of Nexus switching and need to focus more on just the specific data center topics, things like virtual port channels, VDCs, overlay transport, virtualization, a lot of the things that are at this point basically cutting edge technologies that are just starting to get deployed and starting to get introduced with these platforms. That's going to be more of the focus for this first module with the Nexus switching. The other two, however, with the storage and the computing, like I said, most engineers don't already have a background for this. So if you're already strong with Nexus, then you can skip that. Just go to storage or just go to computing. Or likewise, maybe you're not even going to take the CCIE Data Center exam. I just want to learn, you know, what is Nexus? How do I deploy this in my day-to-day job? And really that's what is going to be one of the big focuses of how we're actually delivering the training, how we're delivering the instructor-led training, the self-paced, and then like lab material, rack rentals, is that you'll be able to pick for either your certification preparation or for your day-to-day engineering, what are the specific topics that I want to learn and really what's going to apply to me in the real world. So like Mark said, the first of these topic domains is going to be Nexus switching. So from a very high-level overview, the first thing is that the Nexus is basically just a layer 2 switch that has layer 3 routing capabilities as well. So most of this is going to be very straightforward for a lot of engineers. Things like how do access VLANs work, how does trunking work, how does ether channel work, how does layer 3 routing work. Most of that is going to be no problem for most people. Now when we look at the more enhanced features that are specific to the data center environments, this is typically where people want to focus nowadays. Where the first one we have here is a feature known as virtual port channels or VPCs. And if we take a look back at our diagram here, we can see that there's a large physical mesh of the cabling that's going between the platforms. And in traditional environments, what we would have is maybe one Catalyst 6500 talking to another Catalyst 6500 with multiple gigabit Ethernet links or possibly even 10 gig links, that we're taking these physical Ethernet links and then we're binding them together logically with an ether channel or a port channel. Now the design limitation of that traditionally is that it only goes between those two physical chassis. So if one of the chassis goes down, or if there's a cable problem, or there's a line card problem, it means that your entire channel is going to be lost and you won't be able to forward your traffic. So the next iteration beyond regular channeling or link aggregation that Cisco came up with is this feature that's known as virtual port channels.
And you may have even worked with it in the Catalyst 6500 line. It would be called VSS, or Virtual Switching System. It's similar, although not exactly the same. It's going to have a similar idea to it.
Right, so same type of logic with VSS. It would also be the same type of logic for the lower level access switches that do stackwise. Like if you have two 3750s that are connected together through the stackwise cable, when you manage those look like one logical switch that has multiple line cards. So what you could do is plug one cable into one switch, plug another cable into another switch, and then bind those together as a port channel. Then if one of the chassis physically goes down, you're still able to forward your traffic. So same type of logic here with the multi-chassis ether channel or the VSS, but now we're taking the step, taking the feature and the technology one step further. And really the big sticking point with the virtual port channels is that we have two independent control planes in the network. Where if we were to have two Nexus 7000 switches, or two Nexus 5Ks, or two Nexus 2Ks, or even down to the actual blade server chassis, what we can do is have these physical links that are channeled together from a logical layer 2 point of view, where when we look at the case of like spanning tree is going to see these as one physical link in the case of actually forwarding. But when we step back and look at the actual physical view, as opposed to the logical layer 2 or the logical layer 3 design, is that we really have these port channels that are distributed between the different switches. Where
Spanning tree would see this as the same physical device.
Correct. So it's
the same bridge.
Right.
Bridge ID.
So it simplifies from the actual data forwarding point of view. It simplifies the topology and makes it look like we basically have one switch here and we have one switch here that's actually made up of all four of these chassis. But then it's going to give us additional redundancy from a physical port level, or maybe the power goes out, one of the chassis goes down. We're going to be able to still continue to forward the traffic. Now, once we actually get into the details of how does VPC work and how do we configure it, you'll see that a lot of the syntax is very straightforward for a lot of these features, but the potential problems that we can run into, how do we do troubleshooting, what are the different verification commands, that's going to be one of the big things that goes along with this. That what happens if one of these links goes down, or basically the control channel between them, which is known as the peer link, between them, what if one of the peer link goes down and one of the switches is forwarding and the other switch is still accidentally forwarding? We can run into some problems with layer 2 loops in the network.
There's also something called the peer keep alive link. What if this link goes down, but the peer links do not? What if both the peer links and the peer link keep alive go down? There's all sorts of variations, not to mention the fact that we can actually have VPC, or this multi-chassis ether channel, back to back, so we can have two different VPC domains, and they are bridging between them, or we can even have what is called VPC enhanced, or enhanced VPC, where we have hierarchical links. And I'm not sure if that exactly gets into the version of NXOS that's on the lab. I think it's one iteration above that, but we'll still talk about this because it's applicable to the everyday data center. There's even iterations called something called VPC Plus, where we'll talk about VPC and its integration, or all the different fine points that we have to consider with something else called Fabric Path that we'll talk about later. So just this one small domain, this one small topic of VPC has so many different ramifications. Obviously nothing that we'll be going deep into today, but just giving you an idea of one of the technologies and feature sets inside Nexus that we can really unpack to a great deal, great level, and something that we'll be going into in our primer and enhanced classes.
Yeah. I mean, this feature just on its own, it looks very straightforward from the high-level overview, but you could literally do a 5-day class on just VPC. talking about what are the different designs, what are the different failure scenarios, and like Mark said, once we actually get into the classes and the videos, we're going to be going into to more details with it. But this is one of the big selling points of Nexus as opposed to your other traditional layer 2 or layer 3 switches, is that you get to use more of your physical links in the network. So we don't have spanning tree that's saying I have 2 links and one of them is forwarding, one of them has to be blocking. But when we do that, when we introduce that additional step of complexity, then we need to figure out if something goes wrong, what are the actual implications of that in the network. Okay, the next big topic domain is what is known as virtual device contexts, or VDCs. Now, VDC basically is a way to virtualize the physical chassis of the Nexus 7000 series switch, where you may be familiar with this. In the case of layer 3 routers, it's similar to what we could do with a virtual routing and forwarding instance of VRF, where I could have 2 interfaces that are in different routing tables, so they're not able to forward traffic between each other. Or in the case of like the ASA firewalls, we have the security context, where I could take like a ASA 5580, some big chassis, and say, I'm going to break this up into different logical distributions. So I have one customer that has one virtual firewall, another customer that has another virtual firewall.
Or an iOS XR with GSR.
Or
and
right. Or the iOS XR platforms. This is what they call the secure domain routers, the SDRs. But in this case, this is specifically for the Nexus 7000 series switches. Now, what's really interesting about this is that when we look at this from the high-level network design view, we may see when we get to the lab exam or in your everyday practical design, I may have 2 or 4 or 8, multiple different 7000 series switches here from a logical layer 2 and from a logical layer 3 perspective. But in reality, these can all be the same physical chassis. By splitting the port assignments into the different virtual device contexts, I can say that traffic physically to go between 2 ports on the same line card would actually have to go out the link and then come back in, which gives it more security from like a physical operation point of view, but also from a software resiliency point of view when we're comparing it to something like VRF routing in regular iOS.
And VRF routing is something that we can and will put on top of VDCs. Right. So we've got multiple layers of this virtualization. So, and Cisco on the blueprint, as we'll take a look at the hardware in a bit, they list SOUP for their supervisor for their Nexus 7000 series. They don't actually tell you whether it's a SOUP 1 or a SOUP 2. We anticipate a SOUP 1, but it could very well be the newer SOUP 2. With a SOUP 1, we have 4 virtual device contexts per physical Nexus 7K. With the Supervisor 2, we have now 8. So we have the admin or default, which can forward traffic. A lot of times in a lot of data centers it doesn't, but it certainly can. We can break this up by really whatever we want to partition these off for. We can partition them off for our purpose of storage VDCs. We can break them off for the purpose of FCOE. Going along with storage, we can break them off for just multiple different device contexts for multiple different, basically what would look like multiple different switches. So we really could have up to, I don't think that they would do this in the lab, I don't know that you have time to do this, but we could have up to at least 8, with 2 physical boxes, 8, or technically with a SOUP 2, we could have up to 16 Nexus 7000 switches, bringing this simplified, and I'm not sure if this topology looks simple or not, but if it doesn't, just wait till we add virtual device context. So there's really no end to the different types of overlays and topologies and topics that we can talk about.
So going along with what Mark said, and as I was mentioning before, the flexibility of the platforms, you'll see once you get into the details of like the Cisco validated designs and the different just overall topologies that you can build with the Nexus 7000, you may have it up here in the top of the network as your core layer 3 switching, like where your default gateways are going to be, but you could also have the same physical chassis where I have basically VDC 1 over here, VDC 2 over here, that's doing my layer 3 switching, but then as opposed to using the Nexus 5000, I could take that same physical platform and run 2 separate VDCs down here. I could have VDC 3, VDC 4, and then I could use this for my layer 2 aggregation as well, So I could have one physical chassis that's both the core of the network and the distribution layer, or technically down into the access layer, where we have high-density 1 gig Ethernet line cards and high-density 10 gig Ethernet line cards. There's also now 40 gig Ethernet and 100 gig Ethernet line cards that are available for the Nexus 7000. So there's a lot of flexibility that you can do with this. And again, it's one of those features, just like VPC, that from the high level, it looks pretty simple, but once you start to get into the details, there's a lot of complexity that they could add within the scope of the lab exam, or in the scope of a real design, what the flexibility you can actually do with this particular feature.
One more thing that we can do with the 7000 and VDC, you wouldn't obviously do this in a real data center, but in a limited lab environment for like the CCIE Data Center exam, they can use these VDCs to break apart logically separate Nexus 7000s that emulate a completely separate, geographically separate data center. Right. And then we can introduce other type of technologies like bridging or switch, layer 3 routing, right. MPLS over the Nexus 7Ks, or something that we're going to talk about called overlay transport virtualization, OTV.
Which actually brings us to that next topic,
Perfect.
The overlay transport virtualization, or OTV. Now, OTV is sometimes called MAC in IP bridging or MAC in IP routing, where if you're familiar with MPLS at all and MPLS layer 2 VPNs, basically the design goal of this is that I have two platforms that are running layer 3 routing. So let's say I have two edge routers that are connected to the internet, and we're routing public IPv4 over the internet, whether this is like an MPLS layer 3 VPN or this is just any connectivity that we have. But the goal of OTV, and let's assume, like Mark said, let's assume that these are physically separate data centers. Like this is Los Angeles, this is New York, and then we have some sort of long haul links that are going over the layer 3 network between the different data centers. So if this is just public internet, or if this is MPLS layer 3 VPN, really as long as we have IP connectivity, that's what we care about. Now, the OTV feature, as it stands now, it's only supported on the 7K, so you would not see this on the 5K or the 2K or any of the other platforms in the design here. But what the goal is that using this overlay, we basically form a layer 3 tunnel.
Layer 2 tunnel.
That is going to be running over, that we're going to be using to bridge our layer 2 traffic. So basically we would have like our layer 3 IP header, but then inside of this we're going to be encapsulating our Ethernet frames. And then we have our final data like that's coming from the end server. So this is similar to other technologies that we've had in the past, like layer 2 tunneling protocol, L2TP version 3, or in the case of MPLS, what we call as the ATOM feature, any transport over MPLS, or the virtual private LAN services, VPLS, where basically the goal of this is that we're trying to bridge the layer 2 network over layer 3.
And all of these have great feature sets. Some of them are more static than others, like L2TPv3. I have to peer, well, I guess we have to peer up my static pseudo wires. With VPLS, you can have multi-point. OTV really gives you up to 2 Nexus 7000s at each site with a current maximum of 3 sites. So we could actually bring 3 sites together, and there's really nothing with VDCs to say they couldn't bring 3 sites together at least on a single set of Nexus 7000s, right. Or even a pair. I mean, that's only 6 switches. We have 8 VDCs between 2 switches if we have SOUP 1s, and even more if we have SOUP 2s. The topology, the logical topology they could build could very quickly get complex. Right. One of the other things about OTV is that it requires a multicast infrastructure. So it's going to be assumed coming into, and we'll talk about the different levels of offerings that we're going to be doing, but it's going to be assumed that you have multicast understanding at or on the Nexus platform. And so Brian will talk about how we're going to have he's going to do some primer classes as well for those that may not have turned on layer 3 routing or done spanning tree, or in the case of what we're talking about, multicast IGMP and PIM in Nexus.
Yeah, specifically in NXOS. So again, going back to this with the layer 2 over the layer 3 tunnel. Really what the overall design goal of this is that from our end servers, which in most cases today are now going to be virtualized, like we're running VMware down here, or maybe we're running something like Xen or Microsoft Hyper-V. That right is there's some OpenStack as well, some of the open source versions of this. But the key is that what we want to do is that if there's additional load on the data center, or maybe there's some sort of catastrophic event, like there's link cuts or there's power outage, fire, something like that, we can take our virtual machines that now have a lot of flexibility, because remember, this whole network looks like just a flat layer 2 LAN from the end host point of view. So we have this layer 2 LAN that's getting us up to the edge, which is the Nexus 7000. We can then take this virtual machine and basically send it over the OTV tunnel and have it come out on a different data center. So we could do what, in the case of VMware, they specifically call this vMotion, where you're taking your virtual machine, then you're transferring it from one physical host to another physical host in a different location. And I could say that, you know, not only are these data centers connected, you know, over the layer 3 network, but they may be geographically huge distances apart. That when my users are coming in, if they're coming in from Los Angeles, and then, you know, if there's some problem in this data center, I could say, you know, move that particular virtual machine over to the New York data center. And the key is that with these enhanced features like the overlay transport virtualization, it gives us a lot of flexibility when we're dealing with basically these flat layer 2 network designs in the data center, which is kind of strange, because traditionally we started with flat layer 2 networks, right? We started with like Ethernet hubs to Ethernet switches. Then we had problems with spanning tree and scaling spanning tree and scaling VLANs and trunking. So the next iteration design was to get rid of layer 2 and put layer 3 everywhere, where we're routing down to the access layer, running OSPF or eEdgeRP on our access layer switches. But now we're actually seeing a reverse of that paradigm, and we're going back to layer 2 bridging, where the whole data center, again, is basically physically very complicated, but from a logical point of view, it's very straightforward. It's just one flat layer 2 LAN, and then we have these physically disparate data centers that we could transfer the basically the workloads of the servers transparently between them using this feature with the overlay transport virtualization.
Part of this can go back to a conversation of, is this a good design? What are the inherent risks of doing that? And some of those things we'll address as we go on in the boot camps. It won't primarily be around that, but we might talk on that some. But the thing to keep in mind is that whether it's a good idea or not, it's possible these days, and people are designing systems like this. And so we have to be aware of them and obviously be able to support them in order to be able to go in and take and complete these tasks in a CCIE data center type environment. So whether it's necessarily the best idea or not may not really necessarily matter. Right. We need to know how to do it, and some of the things, you know, we need to keep in mind what are some of the ramifications of those. So we'll address some of those in the classes as well.
Yeah, like Mark said, you know, there's a lot of other interesting things that come along with this design as well. Because let's say, a quick example, I have my server that's located in LA. Something happens with the LA data center, and I transfer the load over to my New York data center. Since this is a flat layer 2 network, whatever this end server is, let's say I have a web server over here, and its IP address is 10.0.0.1/24. I port this over the OTV tunnel. It ends up on the other side, so now it's on a different physical server, but it's still the same logical virtual machine. So it's maintaining its layer 3 properties. It's maintaining its like default gateway, its DNS, that type of stuff. So now if I have my actual end hosts that are coming in from the IP network, like I have an end user that's in Europe that's web browsing to the server, what happens with this IP address? Okay, we're still using our normal layer 3 routing design here, where we're going to look at what's the route to get to the server. If the Los Angeles data center is advertising this server's address, the traffic that's coming in from, let's say, from London, the traffic is going to come in to LA It's going to go from LA back over the OTV tunnel to New York. From New York, it has to go back to LA and then out to London. So you can end up in these weird designs where it technically works, but it's really not going to be the most optimal design. And what that is going to play into is a new next generation protocol that's still in the process of just starting to get implemented that is known as Lisp, which is the locator or location independent locator ID?
Separation protocol, yeah.
Separation protocol, there we go. Which what this allows you to do is to now decouple the advertisement of the end host address from the actual physical site that it's coming from. Because traditionally in layer 3 designs, like if I were to take a server from this side and move it over to this side, it's not going to work. Because I have different IP subnets, I have different default gateways, I have different routing protocol designs. Right. But now since we're going back to this flat layer 2 network, there's additional things that we need to take into account with this. So this is going to be one of the new big practical applications of the Lisp protocol, is that when we're doing this transfer of the workload from one data center to another, when traffic actually comes in from the end users, I want to make sure that it's routed to the correct physical site. And like we said, we'll get into the more technical details of this in the actual classes, but just kind of as a high-level overview, you can see already just with these 4 line items, and actually really the first one, layer 2, layer 3 switching, you could throw that one out. Just with these 3 line items, VPC, VDCs, and OTV, it's a huge topic scope. So it's definitely more that could be covered in 5 days. We could do a 5-day class just on OTV, or a 5-day class just on VDCs, just on VPC.
Absolutely, and the configuration for OTV not being that difficult, the underlying architecture being the ISIS protocol, the intermediate system to intermediate system, if you're familiar with routing and switching topics, the configuration not being that difficult, the problem becomes, well then if it's really not that difficult of a configuration, why would they put it in a CCIE level exam except to say that it's part of the modern data center or becoming part of the modern data center? Well, take into consideration all the things that could go wrong. And so while you don't need to necessarily know really ISIS to configure, it's things like understanding what's underneath, what's really making it work, which is actually the same technology making something we'll talk about here in a moment, I think next, called Fabric Path, it work as well. Being able to understand these protocols and troubleshoot them will really give you a much better understanding not only of these new coined terms, you know, OTV, whether it's a marketing term or just, you know, Cisco's implementation of it, but really how to troubleshoot and kind of give you an idea of what you might see in the CCIE exam as well, which is, of course, is going to be the complex.
Okay, the next topic, is Mark mentioned here, is a feature that is known as Fabric Path. This is a Cisco proprietary feature that is kind of a pre-standard version of a new protocol that is called Trill, a transparent interconnection of lots of links. Now, the goal of Fabric Path is that for networks that we have a large physical mesh of interconnections or lots of links, that traditionally we run into this problem with layer 2 networking that spanning tree says I may have 1,000 ports, but you can only use one of those for forwarding because one of them is going to be the root port, the other ones are going to be the blocking ports because we need to prevent our layer 2 looping. So Fabric Path, or the next iteration once it becomes available, which is Trill, basically solves this type of problem where we no longer have any blocking links in the network. We're basically allowed to forward on every single physical path. But if we're doing that, we then need some additional mechanisms to make sure that the traffic is not looping through the network.
If I'm paying for 100 gig ports and one sitting in blocking, I'm going to be very unhappy with the cost I paid for that port.
Right. So we're not going to get into really the technical details of how you actually implement this yet, but it is one of those big things that falls into this design that, you know, we have, originally we had just the single links with spanning tree, then the next iteration is we went to port channels, single chassis ether channels, then we went to multi-chassis with either like the VSS and the 6500 or the stackwise cable with the like the 3750 chassis. Then next iteration with Nexus is the VPC. So Fabric Path is taking VPC one step further, or what's sometimes called VPC plus, is basically to say, you know, I don't care how many physical links that you have, I just want to make sure that I can forward over all of them at the same time. So if there's a link cut or there's an extra load on the network, then that's not really going to bother me from an operational point of view. So like I said, you could see just with these few topics that we're getting into so far, there's a lot of detail that we can get into with this. Okay, the next, and then lastly, security. So security is, since the Nexus is still a layer 2 switch, it's also a layer 3 router. It means that traditional security with things like access lists or port security or 802.1x, those are going to be features that are available in there. But there's a new feature that is called Cisco TrustSec that allows us to do encryption at layer 2.
Literally link by link.
Link by link encryption, which is not a Cisco proprietary feature. That is an open standard. But with this Cisco TrustSec design, what it allows you to do is to take some of the previous attempts of this, what was called network admission control, or NAC, which a lot of the times didn't really work out in actual implementations. But the idea of NAC is that if I take my laptop and I go to your network and plug in, you want to make sure that I'm authorized to actually get access to whatever resources that I have. So in traditional networks, it's very difficult to do that because, you know, there's only a limit that what you can do with username and password authentication or .1x authentication. I can give you a username and then you can open the port up to me, but then what do I actually do once I'm on the network, or how do you actually account for what I'm doing on the network? So what this feature allows you to do, Cisco TrustSec, is that when I send the packets into the layer 2 LAN, there's an additional tag that goes onto the header. So as opposed to just trying to enforce this in the control plane, which would be like my username and password authentication, I can now actually enforce the security in the data plane.
At any device?
At any device, at any individual hop in the network. So basically what we have is group-based ACLs that is going to be able to match on the particular security tag that the user is assigned once they log into the network. So I can say whether I'm coming in from wireless or I'm coming in from wired, or whether I'm coming in on my iPad or my iPhone. When those devices connect to the network and associate, they're going to go through this, the network admission control, or like the .1x authentication, and then get assigned the security tag, and then that ultimately is going to control how they can actually forward in the data plane through the network. So this is going to be within the scope of data center. It's not going to be as big as things like VPCs, VDCs, because it's not a security exam. But going forward and in actual practical implementations, this is a really interesting feature. A lot of flexibility that you can use this for your actual implementation of security. And
it's interesting, Cisco didn't include on the hardware, and it could just be an oversight, an omission, but they didn't include either the ACS 5.2 or the ISE, right. We're going to obviously need to have that. So when we talk in our classes, again, as Brian said, it's not going to be a security class. So if you want to learn really how ICE works, the ISE engine, then that's where our Security 4.0 blueprint is going to be able to help you there. Right. But we will include bits of it. We just won't necessarily go deep on that particular aspect. But we will talk about how to encrypt link by link, which is done literally in the actual ASIC, in the switch on chip, in the Nexus platform, as well as how to create these group-based ACLs and deal with it in the switching platform.
Okay, so that then brings us to our next topic, which is storage, which is going to be scary for a lot of engineers out there. Because like I said, WAN engineer doesn't know anything about storage, and storage engineer doesn't know anything about layer 2, layer 3 networking.
And now they're on the same cable.
Now they're on the same cable, exactly. This is really where the marketing term unified fabric comes in. So basically what unified fabric means is that previously, and if we look back at our diagram here, previously what we would normally have on your actual end server is one port that goes to the LAN, like my 1 gig Ethernet or my 10 gig Ethernet, and then one port that goes to the SAN. Okay, the SAN port is going to be running fiber channel. Now, with the next iteration of the data center design, we're collapsing these two together so that the physical end server, or in most cases the logical end server, which is going to be like a virtual machine, the virtual machine is then going to be talking to the end host, or excuse me, the VMware host that's running on the physical hardware. And what it's going to be presented with is just one link. And this is what we call our converged network adapter, or our CNA.
It's really one hardware network card
One hardware network
on the
card,
server
right, on the actual physical
that speaks
server.
both fiber channel, or sorry, speaks both SCSI to the server,
Right.
and then speaks fiber channel or fiber channel over Ethernet out to the fabric, as well as our LAN services, our Ethernet.
Right. So the key here with storage is that from the actual end server's point of view, how do we get them to talk to the storage array, like our EMC or our NetApp, or maybe just some homegrown solution with like OpenFiler, where the servers typically nowadays, basically the only thing that the server is a CPU and a memory box. So we have our CPU, we have our memory. The other resources are coming from the network, or they're coming from the storage, where we're now going to use this converged network adapter, which is going to run the LAN switching for Ethernet, and it's going to run the SAN switching for fiber channel physically over the same cable. So with this then, is going to come into play how do we deal with this on the Nexus platform, and then specifically the actual fiber channel switching platform, which is the MDS series. So this brings us to a lot of new terms for a lot of people that don't have experience with SAN switching in the past, but you'll see that once you get into the nitty-gritty details of storage networking, there's a lot of the concepts that come from LAN switching are going to be ported over to SAN switching. Like we have the notion of a virtual SAN or a vSAN. vSAN would be analogous to a VLAN.
And in fact, it requires a VLAN to run the vSAN.
Right, right. Where with VLANs, we're using those to limit our failure domain, to limit our layer 2 flooding domain. Basically the same thing with a vSAN, except we're running it inside the fiber channel protocol as opposed to Ethernet. We also have fiber channel trunking. So if I have two switches, they have multiple vSANs, similar to two LAN switches that have multiple VLANs. I need to talk over the trunk link with them. We also then have a feature that's known as zoning, which could kind of be considered like access lists on the routers, where what this is used to do is for our actual end server. So the end server is trying to address some physical disks that exist on the array. The array is going to present this with what's known as a logical unit number, or a LUN. This basically means the volume that the server is going to mount. Like if I go to Windows and I go to my disk management, if I see disk 1 and it says disk 1 is whatever, 100 gig volume, the server doesn't need to know that physically that disk is not actually attached to your hardware. But in reality, the disk is going over the SAN and it's being addressed inside the array based on this logical number, the LUN. The potential problem you run into with this, though, is that we need to make sure that the server is talking to the correct disk volume on the actual storage array.
We also need to make sure other servers aren't talking to that same array unless they're intended to.
Right.
Because then we could get into a file locking issue. We could get into an issue where we have multiple platforms maybe writing their disk signature. Windows is going to write its own disk signature. Mac is going to write its own disk signature. So.
And that's basically what zoning is used to solve. So zoning is going to say, once we get into our layer 2 switching, like let's say we're talking about this on the MDS, the MDS is going to say that this end server is going to be assigned what's similar to like a MAC address in Ethernet, what we call our worldwide port name, or the port's worldwide name. It's basically like a hardware address that we have for fiber channel. Then what the switch enforces, it basically says that this port name, let's say it's A, goes to this particular zone where the zone is associated with that logical unit, and it allows the server to mount the volume. And then, like Mark said, it also prevents other servers from mounting that same volume. So it gives you centralized control inside the fabric of the network, or basically on the MDS or on the Nexus switches, to control the end servers. How do they actually talk to the storage arrays?
And this fiber channel is going to have its own worldwide port name or port worldwide name. So it's almost like saying logically in the vSAN or in the storage fabric this port can talk to this port, and this port is literally just a disk. And that's how we're going to marry those two up and make sure that no one else can talk to them unless intended. And that's the concept of zoning, is having, you know, a port or worldwide port name from the fiber channel attached and allowed to only talk to the worldwide port name of what's called an HBA, or a host bus adapter, basically the fiber channel SCSI-based storage addressing the server.
So then we also have, specifically with the Nexus and with the MDS switches, something that's called the Cisco Fabric Services, or the CFS. You could kind of think of this like VTP for SANs, where in the case of Ethernet switching, we have the VLAN trunking protocol that's used to advertise things like VLAN names and VLAN numbers. It's basically just for management of the devices. Cisco Fabric Services can do the same thing, basically where if I have multiple physical switches in the network, and I'm trying to make sure that this server is only allowed to talk to this specific volume on the SAN, I need to make sure that everyone is actually enforcing this with the zoning protocol. So from a management point of view, it's going to be difficult to keep track of what are all of basically the MAC addresses, like the worldwide port names of the servers, and then mount those or map those to the individual volumes.
On every hop.
On every single hop, exactly. Right. So it's basically like doing a VLAN ACL in the case of LANs, but you'd have to do it on every single switch in the network.
So the Cisco Fabric Service is going way beyond just VTP, which is propagating the vSANs. It's doing not only that, but it's also propagating zoning, and it's even doing other additional things like maybe NTP or other things beyond the scope that a normal VTP would do on a standard Ethernet fabric.
So we'll get into this obviously in more detail once we actually get to the storage classes. But from a high-level overview, these are some of the similarities that we can kind of make analogies between the LAN world and the SAN world.
And I think it's probably worth noting, we had a question on the chat, I think it's probably worth noting that this is not the CCIE SAN, nor is it yet. At some point it may, we're not really sure, no guidance on that from Cisco, but it's not yet replacing the CCIE storage, or CCIE SAN as some people colloquially call it. Right. So this is, we're not going to go as deep into just storage as they would go in the CCIE SAN, where they have an entire 8-hour lab plus your written exam before that, just based on storage. We're not going to go that deep, but we did break it apart into its own topic domain because, as Brian said, we feel that the average engineer coming into a data center for the first time, or even possibly the average data center engineer that might be familiar with, let's say, Nexus switches and fabric, may not be as familiar with the fiber channel protocol. And while we may not have 4 hours worth of configuration of this in the lab, it's very important that the 1 hour or 2 hours or whatever it might be of configuration or worth of tasks of configuration that we might have, that we actually really understand it and can implement it quickly and get it out of the way and focus on what's probably going to be the majority of the exam, which is the Nexus and the UCS. Right. But we need to understand storage, so we broke it into its own topic domain.
Now, if we were to take this from like a practical functionality point of view, let's say an example from the point of view of the exam, we could have a lot of these pieces are going to fit together in order to get our final end result. So let's say theoretically we have exam questions that say, get on the UCS chassis and configure a profile that assigns a server to an individual blade in the chassis. When the blade boots, it needs to talk to the SAN in order to get its OS. Let's say we have like a Linux volume that's pre-built on the fiber channel array. The problem then becomes
something
if
called boot from SAN.
Boot from SAN, right?
It's not even going to boot up if we don't have the storage.
Exactly, exactly. So your actual end server functionality, this is real easy for them to test within the scope of the exam. Get on to basically the KVM interface of the server. The server doesn't boot, means your storage is broken, or maybe your Nexus switching is broken. So there's a lot of individual pieces of the puzzle that are going to fit together for this, and it really, like Mark was saying, to understand this, you have to break them apart and take them in their individual building blocks and make sure we understand at a fundamental level what is fiber channel. What's the difference between running native fiber channel versus trying to tunnel it over IP with FCIP? Or what's the difference between getting rid of fiber channel completely and just running our native SCSI over IP, which is iSCSI. And then we also have our fourth variation, which is the newest version that comes along with that unified fabric, which is taking fiber channel and then tunneling it directly over Ethernet. So I would imagine the last point here, the FCOE, is going to be a larger portion of the data center exam, because this is really the next step that we're trying to take with this overall design. That we're trying to take these end servers, collapse them down so we have less physical wiring in the network. We're replacing these NIC cards and the HBAs, where HBA is like your NIC for SAN. We're replacing this with the CNAs, the converged network adapters, that's going to run both our storage and our LAN at the same time. But this last topic, the FCOE, there's additionally a lot of other things that come into the design, where Fiber Channel originally was a lossless protocol, which means that if I have a database application, let's say I'm running SQL on this server, and my SQL needs to write to the disk array, I need to make sure that that write actually makes it there. So in the case of Fiber Channel, it's not like TCP, you cannot retransmit. So in the case of Fiber Channel, we need to guarantee that the transport is there. The problem now becomes we're taking Fiber Channel and putting it over Ethernet, which inherently is a lossy protocol. That we already have applications like hopefully not lossy. In practice, a lossy protocol. Right. But we already have at the application level, or like in layer 4 with things like TCP, we're already dealing with the retransmission and the error correction. But the problem is now that we're taking what used to be a layer 1 lossless protocol with Fiber Channel, putting it over Ethernet, and then there's additional things that need to come in to the design with that. We have a new Ethernet standard that was ratified not too long ago, which is known as Data Center Bridging, or DCB. It means that these switches need to support a special negotiation that will tell them on the inter-switch links, or basically the trunks, that I can guarantee that your Fiber Channel traffic is not going to be dropped when it comes in.
On a traditional MDS switch, we have something called buffer-to-buffer credits, which basically says that link by link, I'm going to stop, or I'm going to inform the Fiber Channel, the HBA from the server, to stop sending data if I become too congested. Just pause, just hang on a second, and then as soon as I get enough credits, I'll allow that to continue. Well, with Ethernet, traditionally, there is no pause. Right. So part of data center bridging are things like .1Q BB, .1Q AU, .1Q AZ. All protocols will be unpacking, as well as something called pause, where the Ethernet can actually, or the switch really through Ethernet can actually signal to pause sending Ethernet frames, but only to a very specific class. So all this gets into very advanced quality of service, and quality of service will be, if you think you know quality of service and you haven't got into the Nexus line, just wait, it's a whole nother level to unpack. But we're going to, of course, go into that quite as well. So that really ties the storage back in with the Nexus line, and we have to go back to the Nexus and understand QoS really thoroughly. Right.